This is a video about one-dimensional kinematics, motion maps, and the kinematic strategy. First of all, let's look at the direction conventions. Conventions are just the normal way that we do things. So up is always positive, to the right is always considered positive. These are just directions. Down is negative, and to the left is negative. We're all familiar with the compass rose. Upward is north, down is south, east is to the right, and west is to the left. And also, notice the direction in which we point 0. We point 0 degrees directly to the right. Now, as we go over these definitions in all these videos, you don't need to memorize them, but you do need to know how to apply them. Okay, so the first definition we'll go over is position. A position is an object's location relative to some other arbitrary point. So put position there in your notes. Okay, so we don't need to memorize it. We just need to know how to apply it. So what's the position of the dog relative to the reference point? Now we consider the reference point to be here at 0 meters. So the dog is to the right of the reference point. So we would say that the dog is at plus 5 meters, or we could say that it is 5 meters to the right of the reference point. Now what about the cat? We could either say that the cat is -8 meters relative to the reference point, or we could say that it is 8 meters to the left of the reference point. Okay, because we have to give the direction. So for the cat, we're saying it's to the left, and negative means it's to the left. For the dog, we're saying it's to the right, or that positive is to the right. They mean essentially the same thing to us. Okay, so the next definition is the change in object's position from the very beginning to the end. Okay, so it's always relative to where it started from. We call this the displacement. And all that matters for displacement is where are you relative to where you started. The total length traveled from the beginning to the end is called the distance. Okay, again, we don't need to memorize these, but we do need to be able to apply them. So in this example, it says the dog walks from the plus 5 meter location to the cat's position, then it runs to the -3 meter location. What is a dog's displacement, and what is the distance that it's traveled? Okay, so first let's look at the displacement. Okay, so displacement, another way that we would write it is in an equation like this. The final position minus the initial position. Okay, so the final position of the dog was at -3 meters. Its initial position was at +5 meters. So I'm going to subtract the +5 meters, and that gives me a value of -8 meters. Or we could say that its displacement is 8 meters left. As long as we understand that that's what the negative sign means. Now, that answers the displacement. Let's figure out what the distance traveled is. Okay, so if there's two parts to the dog's travel, or little trip here. Okay, in the first part, it went 13 meters. It went from the -8 meter position to the +5 meter position. But for distance, direction doesn't matter. So we just say that it traveled 13 meters in that part of the trip. In the second part of the trip, it goes from the cat's position, which is right here, Okay, then finally over to the negative 3 meter position, which is right there. So in the second part, it's only traveling 5 meters. Now, again, direction doesn't matter. We don't care whether it's to the left or to the right. The total distance it traveled, therefore, is 18 meters. Okay, and we don't say to the left or to the right because direction doesn't matter. So it's a total length that's traveled of 18 meters. So notice for displacement, all that matters is the beginning and the end. But for distance, everything in between matters as well. The total length matters. The final question is, which of these is a vector and which is a scalar? All right, so position is a vector. Position is a vector because direction matters. Displacement is a vector because direction matters. Distance, however, is a scalar because because direction is not something that we need when we look for an object's distance that it travels. Okay, and the reason why that is, it all has to do with direction. Okay, 2 of them depend upon direction and the third does not. Let's now go on and look at motion maps. Now, motion maps, I think, are extremely important in kinematics. Make sure that you always draw your motion map, especially when you get stuck. Now, in motion maps, we use dots and arrows. Each dot or arrow represents a specific unit of time. For example, 1 second. It could be 1 hour. It could be anything. But for the most part, we use 1 second. Now, when an object's at rest, we symbolize that with a dot. When an object is moving, it therefore has a displacement, so we will symbolize that with an arrow. Okay, so down here it asks us to draw a motion map for the car below. We're assuming that it's moving with to the left. It says that the same amount of time elapses between each image and the next. So here's how we would draw this. Its displacement would look like that. It's being displaced that amount at a certain amount of time, and I would label that with velocities because we're saying that that's happening over a 1 second interval, if you will. Okay. Another motion map would look like this. Let's take this object on the left-hand side, and let's say it's being dropped at the 0th second, at the very, very beginning. It's not moving. So we'll label its velocity with a dot, meaning that at the beginning, it started off with an initial velocity. We would label that as initial velocity of 0 meters per second. Then it travels that far with a certain velocity, and we notice that the velocity increases on the way down. And based on our conventions, we would say that these velocities, all of these velocities, are negative because they're downward. Now, this car down at the bottom of the screen, we would show it moving. Let's assume that its initial velocity is non-zero. In other words, it's moving. Its motion map would look like this, where it looks like it's coming to a stop. So its velocity vectors or displacement vectors would look like that. And the final velocity would be 0 if we assume that it comes to a stop. So these are just some examples of some motion maps. Okay, now in this motion map, it says a bicyclist rides her bike at a constant velocity of 1 meter per second from left to right. Draw her motion map once she crosses the reference point for 4 seconds. So here's the reference point at 0 meters. So once she crosses it, we would draw a vector like this. 1 meter per second, every second. So she covers 1 meter every second, and we'll do that for 4 seconds. We want to know what her velocity is and her speed, and look at the relationship between them. So her velocity, it turns out, because she's going 1 meter every second, her velocity is essentially 1 meter per second. Her speed is also 1 meter per second. But I've made a mistake here. I forgot to label the velocity with a direction because velocity is a vector. So I should include plus 1 meter per second, or I should say it's 1 meter per second to the right. So either of these would be a correct way of identifying the velocity. So these are two ways of identifying the velocity, and this is how I would identify the speed. Notice the speed does not have any direction. So the velocity definition is the change in position or displacement over time, and the speed definition is a total distance traveled over time. Now in class we'll look at a version of it, I should say a different example of this in which the velocity and speed are significantly different. Here they seem pretty similar. So let's look at now the equation for velocity. All right, so our velocity equation, because it's the change in position or displacement over time, remember our symbol for displacement is delta x. If we go over a change in time, we would call this the velocity. That's the equation for the velocity. The equation for speed is a total distance d, you can use uppercase or lowercase, over time. Okay, so those are two different equations. Notice they're very similar, but again, we'll talk about what the difference is in class. So if we were to determine the displacement using the equation, so the displacement in this case would be delta x. If I rewrite that algebraically and I cross multiply, I would get v times delta t. Her velocity, like we said earlier, was 1 meter per second. And that was happening over 4 seconds. So her velocity would be 4 meters per second. So that would be calculating out the displacement using that particular equation. Notice we would get the same example using that equation for distance. Oh, you know what? I should emphasize here that this is positive because the velocity is to the right. Now, it says down here to determine her displacement using the motion map. Well, that's real easy. If we just go up to the motion map, notice that she gets to the 4 meter mark in 4 seconds if she's going 1 meter per second. And that just makes sense. All right? So that's how we can use a motion map to help us solve these problems. Now, let's look at acceleration. So let's say this time she starts from rest at the reference point and moves to the right. However, every second the bicyclist's speed increases by 1 meter per second. So let's say this is the reference point. We'll label that as 0 meters per second because she's not moving yet. And we'll put a v there to show her velocity. Then 1 second later, because her velocity increases by 1 meter per second every second, her velocity is now 1 meter per second. Then another second later, her velocity is 2 meters per second. And then another second later, her velocity is 3 meters per second. Okay? Now, if we look at how much her velocity changes from second to second, we'll notice a certain pattern. So from 0 to 1 meter per second, her velocity changed 1 meter per second in 1 second. From 1 meter per second to 2 meters per second, once again, her velocity changed 1 meter per second in that 1 second. And once again, from 2 meters per second to 3 meters per second, it went 1 meter per second every second. Okay? Now, these values up top here, we would call those acceleration. To simplify each of those, we would write them down as 1 meter per second squared, and we call that the acceleration, how much the velocity changes. So our acceleration definition is the change in velocity over time, and that would be, if we were talking about average acceleration, that would be at x final and x initial. So it would literally be the change in velocity over the change in time, which would equal v final minus v initial over t final minus t initial. What's the equation for acceleration? That's essentially it here. The acceleration is equal to the change in velocity over time. For this particular example up here, the acceleration is equal to 1 meter per second squared. Here are the kinematic equations. So you're going to be asked to memorize the kinematic equations. There are the three. The initial velocity is v sub 0, the final velocity v sub f, or just v in this particular example. The acceleration is a, the time is t, and the displacement or distance is x, depending on the situation. Really, it's a displacement. Notice the one thing we didn't include was this x initial. Now, most of the time, x initial equals 0 if we're assuming we're starting at an initial position of 0. Okay, but you need to check the problem to see whether the initial position really is 0. Most of the time it will be. Okay, so let's look at this exact same example where we're having this person starting from the reference point and her velocity increases by 1 meter per second. Let's say we want to find out what the bicyclist's velocity is after 3 seconds. Okay, so here we want to use what's called the kinematic strategy. The kinematic strategy means we draw the motion map. So there's a motion map up here. It's already drawn out for us. All right. Then we write down the 5 kinematic variables: x, v initial, v, a, and t. Okay, so we've done that. We identify which variables are known and unknown. The distance that we travel, we don't know that. Okay, the initial velocity tells us it starts from rest, so the initial velocity is going to be 0 meters per second. The final velocity, that's what we're looking for. The acceleration, we figured out earlier, was 1 meter per second squared. And the time, in this particular example, is 3 seconds. So what we do is we circle the 3 variables we know, v initial, acceleration, and time, and the one we're looking for, final velocity. So we need to find an equation that has all 4 of those variables. So the equation that has all 4 of those variables is this one right here. V equals v initial plus at. So if we plug into that equation, we get that the final velocity is equal to the initial velocity, which is 0 meters per second, plus an acceleration of 1 meter per second squared, which we figured out earlier, times a time of 3 seconds. So the final velocity is 3 meters per second. Okay, so that's a very simple version of the kinematic strategy. We'll do more complex ones in class.